Excellent, thank you. So this is a collaborative project with this host of people here. And yeah, I guess we're looking at how things around Antarctica and the ocean change when the wind changes, which is surprisingly not that well understood yet. Okay, so in case people aren't familiar with ocean dynamics around Antarctica, this is sort of giving the basic outline. I think there's no one on Zoom, so yeah. Okay. So we have dense shelf water formation, so strong winds blow sea ice away from the coast, forming linears, open areas, and sea ice. You get large heat loss from the ocean, brine release as sea ice forms, dense shelf water formation, which overflows to form Antarctic bottom water. Sitting off the shelf, we have this warm circumpolar deep water. I'll try not to do too many acronyms through the talk, but these two might be worth remembering. So there's no sort of easy way for that circumpolar deep water to get up onto the shelf. There's no mean geostrophic flows, and so it's transient processes and small-scale processes that bring that warm water up onto the shelf. So things like eddies, tides, flow-through canyons, which is difficult to model and observe. The scale is involved. So we also have strong easterly winds that blow around the continent. That's all I need there. Okay, so all these processes, I'll just give you a bit of a picture of what some of them actually look like and the scales involved. So here we have an example of a polynya. So you can see this is in the Ross Sea. As the winds are coming here, blowing the sea ice away and opening up this polynya here. Overflows. So you can see the mixing that occurs. Really awkward spot to stand. Mixing that occurs as these overflows flow down the slope. This is a particularly difficult problem to model because of the way that the bathymetry is resolved in the model. It ends up being steady, and so you end up with too much mixing, usually in models. Eddies, so around Antarctica, you sort of need to get to sort of 1 kilometre or so resolution in order to resolve the eddies, because the Rossby radius gets smaller as you go towards the south. And this is crucial in order to get this transport of warm water up onto the shelf to resolve these eddies. I guess the Antarctic slope current occurs along this narrow band where the slope is steep around Antarctica. It's also challenging just to get that bathymetry right there. And then there's all kinds of sea ice processes that are very small scale, with sort of fracturing and so on, that are important. And so to give you an idea of how these processes might look compared to the resolution in a CMIP style model, so just drawing these red boxes on, which sort of indicate a grid box size in a typical CMIP style model. And so you can see that in a usual climate model, none of these processes are being resolved, and yet they're all crucial to getting the circulation right around Antarctica. And I guess the difficulty is that, as I'll go on and show you in the talk, not only do you need these small scale processes, you also need the large scale processes, the connectivity between different regions of Antarctica as well. So it's not really enough just to get a regional model where you might be able to resolve these processes. You also need the whole of Antarctica to get the connections between the different regimes around Antarctica. Okay, so why do we care about this ocean circulation? So Antarctica is melting, particularly in West Antarctica and some regions here in East Antarctica, and is being largely driven by ocean warming. So I guess while we know that the ice loss is being linked to ocean warming, we really don't understand completely what the mechanisms are that are driving the ocean warming at the moment. And also, we don't know how the ocean temperature is going to change in the future around Antarctica, partly because when we try and model it, which I guess is our way of projecting, we need to resolve all these processes that I just showed on the previous slide, and that's difficult. So just kind of to put this in context, so I guess the sea level so far from Antarctica is quite small, so it's less than a centimetre. And in the future, if we look over sort of this century scale, the sea level rise coming from Antarctica is not the largest contributor, so it's not as large as thermal expansion or Greenland or so on, but it contributes the largest uncertainty to projections of sea level. So in a high emission scenario here, you're looking at somewhere between 0.6 and 1.1 meters of sea level rise by the end of the century. And that's a huge range of uncertainty if you're trying to adapt to that. And most of that uncertainty, or half of that uncertainty, comes from projections of Antarctic ice melt. So I guess it's really important that we try and narrow this uncertainty so that it's easier to adapt in the future. And I guess one more thing to say here is that, so these projections of Antarctic ice melt come largely from sort of CMIP style models where you take the ocean forcing from CMIP style models. And those models are not incorporating all of the dynamics that you need to actually get that temperature response right in the ocean. So there's maybe even more uncertainty there coming from the ocean that's not even included here. Okay, so onto some ocean modeling. So I'm going to be talking about some runs from Access OM201. So this is a 10th degree MOM5 based model, size 5 sea ice. And I'm going to be talking about some simulations which are forced by a repeat year forcing. So we take 1 year out of the forcing and have a control run where we just loop this same year of forcing over and over. And that gives us a nice stable base run from where we can branch perturbations and we don't need to worry about natural variability in the control to detect signals from. So this model does quite well compared to observations. This is temperature on the left, salinity on the right, and the left of each panel is observations. So you can see that Axis OM2 gets this warm region in West Antarctica, and things generally look pretty good, especially given that the observations are very scarce. There's large regions where we don't have observations, like here in East Antarctica, there's a bit of a gap. So this model also looks pretty good if we look at the circulation, so the overturning circulation. So shown here is where we form dense water in the model. So we form dense water in the same 4 locations that we see in the observations. And this is the age in the model. So this is showing where young, recently ventilated waters are descending down the slope. And this is at the bottom. So this is, these waters in the model do actually get down to the ocean floor. They don't, in a lot of models, the waters overmix and end up somewhere in the intermediate layers. And if we compare the magnitudes, so this plot here is showing, so if we sum around the 1,000 meter isobar, this black line here, and in density classes, sum that from the bottom up. So we have about 10 spare-drops of dense water that flows down across the 1,000 meter isobar, and then return flows of the warm and surface waters southwards. And this compares pretty well to observational estimates of that transport. Just to give you a picture of what these dense water overflows look like. Imagine most of you have seen this movie before. This is in the Ross Sea, and this is just picking out a very dense isopycnal. And so you can see the 3 troughs that flow out of the Ross Sea here, and the dense waters descending down into the abyss across those troughs. Okay, so onto the science. So this is a collaborative project. Now I know a lot of projects we normally do a collaborative. This was a particularly collaborative project with these lovely group of people here. And so basically what we did, we met once a fortnight for a 2-hour block having a hackathon together. So we would sit down and all code on Zoom together, discuss science, and everything was recorded on GitHub. So we listed issues of new types of analysis we wanted to do, put plots into each of those issues and discussions and feedback. And then when we got around to writing the paper, which is nearly done, we also had to go out doing that to a hackathon as well. So we all got into Overleaf at the same time and wrote away together. constantly in contact with everyone, doing everything together, sharing code. Yeah, it's fantastic. Okay, so we've done these wind perturbations. And so before we go into showing you what happens, I just want to talk about what's known before. What do we expect when we do this? And so Paul Spence had this nice study in 2014 where they shifted the winds. And so I guess shifting the winds has the effect that the easterlies get stronger as you get towards the coast. So if you shift them, you end up with weaker easterlies in the coast. And if they're further north, you have stronger easterlies. And so this had the effect as you shift them south, your Ekman pumping downwards at the coast decreases. And so you end up shoaling your isopignals. And because you have cold water overlying warm waters, if you're shoaling those isopignals, you end up with cooling at the coast. Sorry, that's run the wrong way. So when you have stronger easterlies, we have more Ekman pumping. We deepen our isopignals, and so we push our cold surface waters downwards, so we have cooling on the coast. So that was one thing we might expect. And so this is just a purely zonal perturbation, just to say. There haven't really been any studies looking at what happens when you change the meridional component of the winds, and I'll go into that a bit more. So the other previous experiments, this is from an idolized model, and so this is Stewart and Thompson 2012. And so what they did here is just change. This is the strength of the easterlies here. And so they found the green is the overturning across the slope, sort of this circulation here. And they found that as they increase the easterlies, so more negative, the overturning increased. And this largely followed the Ekman response. So you're increasing the easterlies, you get more southward transport of the surface, more upwelling from below, and this increases your overturning. Okay, so what we've done is to do two wind perturbations. So we take, this blue line here is the dividing line between the westerlies in the north and the easterlies in the south. And so we take the winds south of that dividing line and amplify the wind speed by plus or minus 10%. And you can see down here so all the previous studies have largely been focused on this easterly component. But the northward meridional wind is often as strong regionally as the easterlies. Okay, so what happens when we change these winds? So to start off, this is looking at sea level response averaged over the continental shelf around Antarctica. And so I guess what we expect from just increasing the zonal component is that if you increase the zonal component of easterlies, you get more southward transport, and your sea level will increase because you're piling up more waters on the shelf. And so if we look, this is initially what we see in the first couple of years. So higher sea level and generally negative sea level response in the decreased wind experiment. However, as we go further along in the simulation, we actually get the opposite response to this. And we get this decreasing in sea level, which is the opposite of what we expect from here. And we can understand this a bit more if we look at how the abyssal overturning circulation is changing. So you can see that, so we have this is dense water export across the 1,000 meter isobar. So in the control, we have around 9 spare drops, and this increases as we increase the winds, the opposite as we decrease the winds. And so this is consistent with the sea level response that we're seeing over the longer term. So as you increase that abyssal overturning, you're going to bring up more circumpolar deep water, so more warm and salty waters onto the shelf, which will result in a steric decrease in sea level as you have generally denser, saltier waters over the continental shelf. Okay, and just to show a bit more about how this affects properties on the shelf. So this is showing the age change. So when we increase the winds at the top here, you can see that there's a decreased age in the abyss following the dense water pathways. And so this is more ventilated waters reaching the abyss, younger age there. Interestingly, on the shelf, we see these regions that actually increased age, sort of aligned with where the dense water formation regions are. And so what's happening here is that you're getting that feedback response of the overturning. So as you bring more of the circumpolar deep water onto the shelf, as you increase that overturning, you're bringing the older circumpolar deep water onto the shelf. And we actually see this increase in age, despite these waters being more ventilated, because you're increasing the dense water formation, you're bringing more of that circumpolar deep water on, and you increase the age there. Okay, and salinity is in agreement with what we just said before. So generally, as we increase the winds, we get higher salinity on the shelf, which makes sense with our decrease in steric sea level over the longer term. Okay, so if we go back to what I said before about what we were expecting as we change the winds. So the Stewart and Thompson study, we were expecting an increase in the overturning as we increased the easterlies. And they said that was due to this change in the Ekman transport. So more southward Ekman transport, therefore you bring more upwelling up and increase the overturning. So we wanted to investigate this a bit further to check if this is actually the case. This is actually why the overturning is increasing. And so we came up with 3 different mechanisms to investigate to understand if that's actually what was going on. So the first one is that Stewart and Thompson mechanism. So as you increase the wind stress, you increase the wind stress curl and you bring up more waters upwelling on the isopycnals. And this brings more salt onto the shelf and a feedback of increased abyssal overturning. The second one we considered, so the dense water in the model forms in these localized 4 polynya regions around Antarctica. And so we thought that maybe because we're increasing the winds everywhere, maybe you're just blowing more sea ice away from the shelf, opening up those polynyas more locally, and therefore forming more dense water. And the third one, third hypothesis that we considered is that actually, as we change the winds, we're changing our export of sea ice off the continental shelf. So as you increase that meridional component of the winds, you're blowing sea ice away from the continent more on a more sort of larger scale. And this leads to more open water, so less sea ice over the shelf, and therefore increased sea ice production and a feedback increase in the overturning. And so we can go through each of these mechanisms and see what's going on. So the first one related to the winds and the Ekman upwelling. So this plot here is showing a curtain around the 1,000 meter ice path around Antarctica and showing temperature. So this is the warm region of West Antarctica here. This is the Weddell Sea. So we've drawn in this isopycnal here, which is sort of the cap of the warm circumpolar deep water around that ice path. So if we're expecting more upwelling circumpolar deep water on the shelf, it would be happening at densities denser than that line there. And this plot down here shows the Ekman pumping binned into density. So we take the surface Ekman pumping on a monthly timescale. So we bin in time and space into density. So we can figure out which isopycnals, where they are from experience, what amount of Ekman pumping. And so if we look, so basically, yeah, so further north you have Ekman upwelling, drawing water up throughout the Southern Ocean. And then as you get closer, as you get denser, so further south, you have downwelling near the coast as those easterly winds are pushing those isopycnals down near the coast. And if we look at the relevant isopycnal here, which kind of falls in around here, you'll see there's actually downwelling in those circumpolar deep water classes. And as we increase the winds, the blue, that downwelling actually increases. So this casts some doubt on this hypothesis that it's an increase in the wind stress and Ekman upwelling that's causing this increase in the overturning. There's still some doubt there because I guess you can have density gradients within the surface mix layer. And so taking the Ekman pumping at the surface and relating that to isopycnals in the interior might not be the exact right thing to do. So we'll come back to that in a moment, but at the moment, we'll just cast some doubt on that one. So the second one is looking at whether it's just a local enhancement, so the local winds over these 4 polynya regions. And so what we've done here is an additional experiment where we increase the winds everywhere except these yellow boxes here, where we have the local dense water formation. Okay, and so what you can see here, so this bar plot represents the 4 dense water formation regions around Antarctica. And so if we go black to blue, that's as we increase our winds. So you can see that as we increase the winds, we get more dense water formation in each of those 4 regions. And then if you compare the blue to the purple, so the purple is where we don't change the winds in these yellow regions, but we do change them everywhere else. There's largely no change between the blue and the purple bars, implying that it's not the local winds over those polynyas that's driving the change in the overturning. It's more of a large scale response. So we can rule out that hypothesis. Our third hypothesis is related to large scale export of sea ice by the meridional winds. So if we look at what the sea ice is doing, the colours here are showing the change in the thickness of the sea ice. So as we increase the winds, we get largely decrease in the thickness of the sea ice close to the coast, and the opposite as we decrease the winds. The arrows here are showing the sea ice velocities, so indicating the export of sea ice. And so as we increase the winds, you can see that because we're increasing the meridional component of the winds, we're driving more sea ice away from the coast northwards, which is why our sea ice over the continental shelf decreases. So this seems consistent with this hypothesis, except we can, perhaps it's not that conclusive evidence. So what we've done to try and distinguish a bit more between number 1 and 3 hypotheses is to separate the perturbation into a zonal and meridional wind experiments only. So this hypothesis here we expect to come from the zonal winds, because the zonal winds that drive the southward Ekman transport and the Ekman upwelling. And this hypothesis here we expect to be driven by meridional winds driving the sea ice export off the shelf. Okay, so just to remind you, this is what we saw before. So this is just as we increase the winds, we get this increase in sea level initially due to this fast Ekman response, and this slow sea level decrease over the long time scale due to our overturning increase. Okay, and so now if we look at that same plot split into the zonal and meridional perturbations, we find that indeed the increase in the sea level comes entirely from the zonal change in the winds, driving more southward Ekman transport, building more water up onto the shelf. And the decrease in the sea level comes entirely from the meridional component, which is consistent with the sea ice export mechanism. And if we look at how our dense water export changes our overturning increase, the overturning increase comes entirely from the meridional winds. Okay, so we can conclude from that that it's the sea ice mechanism driving the change in the overturning, and that's linked to the meridional winds. Interestingly, this contradicts the Stewart and Thompson hypothesis, who said it was due to the zonal winds. I guess that's an idolized only study. I guess our perturbation uses a much more realistic model. Okay, so then on to understand how this affects the temperature in the ocean around Antarctica. So I guess temperature is what we care about when we're thinking about ice melt feedbacks. So when we increase the winds here, you can see there's some largely a cooling response on the continental shelf. And this was what we expected from the Spence 2014 argument. So as we increase our winds, our ice thickness on the continental shelf shoal against the coast, pushing the surface cold waters downwards and causing a cooling around the coast. You can also see there's cooling in the abyss as we increase our dense water export. We have colder bottom waters. But you'll also note that there's these regions where we get warming on the continental shelf here, which is perhaps a bit less expected. So we can understand those regions of warming by splitting this up into the zonal and meridional components. This is the temperature change from those separate perturbation runs. And so you can see here that these warming patches come entirely from the meridional winds. And the zonal winds, as expected, produce this largely cooling everywhere around the shelf, consistent with more Ekman pumping along the coast. Okay, so yeah, so that's the mechanism here. Consistent with Spence et al. 2014. And the meridional winds, yeah, I guess this is sort of the new part here. And so what we're finding is that, so as we increase our northward winds, this increases our sea ice export northwards, resulting in less sea ice over the continental shelf and more open water, and therefore we can form more sea ice, we get more brine rejection, and this increases our overturning transport, which brings on more heat and salt through something called deep water. And this is what we're seeing in these warming patches here, is that heat being brought back on. And if you remember back to the age that we looked at earlier, we actually saw an increase in age in these same regions here, which indicates this certain quality for coming onto the shelf, driving its feedback. Okay, so how does this relate to what might happen in the future? This is sort of all very idealized perturbations so far. So here there are some seismic projections. And so this is the red lines here, reanalysis products, various reanalysis products over the historical period. And the black lines are the seismic model means. There's actually a spread there, but you can't see that on this screen. So generally what we expect is a decrease in both components of these winds around the continental shelf. These are averaged over that same region south of the east-west dividing line. So this indicates that perhaps our wind minus case might be indicative of what's happening in the future. I guess, so in this case, we increase both the meridional and zonal components equally. Perhaps we might expect more of a contribution from the zonal, which would be more of these warming patches and less of these cooling patches related to the overturning feedback from the meridional winds. Okay, so takeaway messages there. The sign of the ocean temperature response varies regionally due to this overturning response. And this is the same thing we've found. I initially was going to talk about meltwater perturbations here as well, but when we do meltwater perturbations, we find the exact same thing. So there's this local response downstream where we form dense water, where we get changes due to the overturning circulation, and the temperature response there can be very different to the large-scale temperature response around Antarctica. So yes, this is indication that we really need these large-scale models getting connectivity around the whole of Antarctica to get this temperature response right, as well as all the small-scale processes. We obviously need to form dense shelf water formation right in our models to get this right. Seismic-style models that form dense water formation through earth motion convection are not going to get any of these kinds of temperature responses. And in the future, we might expect a weakening of the winds. I guess the caveat there is that weakening of the winds comes from the seismic models, and they don't include things like changing the height of the ash sheet and so on, which might also have large changes on the winds around Antarctica. But if those weakening winds from seismic is what's going to happen, then we expect that to cause a slowdown of the overturning circulation and the warming around the continental shelf. I guess there's some caveats to this model. This model can do many things quite well, such as forming dense shelf water on the continental shelf. But there are many things that are still wrong with this model that we would like to improve. So this is a list of some of those. So at the moment, we're actually inputting all of our fresh water from Antarctica at the surface grid cell rather than at depth, as it should be within ice shelf cavities in the real world. We have no ice shelf cavities in this model, so we just have a wall of the ice shelf cavity fronts. This is something that we're working on improving as we move towards Model 6. This is also only a 1/10 degree model. So as I said before, we need like a kilometre or so to get resolved eddies. So this kind of model is not up to that resolution yet. So possibly we're not getting the response simulated with certain quality water coming onto the shelf correctly. Tides might be important. We don't have tides. We're also working on improving the vertical coordinate. So we do find that at 1/10 degree with the Z-star coordinate, we do still get some overmixing of our overflows. We do get some waters reaching the bottom, but perhaps they're mixing too much as the overflow. So that can be improved as well. Cool. I think I will leave it there with lots of time for questions.